this is where we were. Given a ring R and an ideal I, we define this congruence relation A congruent to B mod I for AB in the ring means that A minus B is in I. This is the equivalence relation on the ring. R mod I denotes the set of equivalence classes which are called congruence classes, also called cosets. Coset of an element A means all the elements of the ring that are congruent to A mod I happens to be the set of all elements of the form A plus X, where X varies over I. This set is denoted by A plus I. And all these cosets are elements of this set R mod I. R mod I consists of these cosets. I think I need this. And we have a bunch of conditions that tell you when two things are in the same congruence class, etc. What we need to do, which is what we're going to do, is we are going to define two binary operations on this set R mod I. That's the goal. Define two binary operations on this set R mod I that turns it into a ring. And the key lemma for that was actually already proved last time. It's written here on the right hand side. Let me read through it. R is a ring, I is an ideal. Let A prime, C prime be four elements in the ring such that A is congruent to A prime mod I and C is congruent to C prime mod I. Then the sum A plus C is congruent to the sum A prime plus C prime, and the product is congruent to the product. So if two things are congruent, two other things are congruent, then the sum of the first two is congruent to the sum of the other two, and the same for the product. The only difference, last time I think I called these four elements A, B, C, D. These names are a little better suited to run through the argument that we will do next. So I just changed the notation a little bit. And I also want to rephrase this a little bit in view of the equivalence given on the left hand side. You see, A plus C and A prime plus C prime are congruent mod I, meaning that the difference is in I. That's same as saying that the congruence class of this guy is same as the congruence class of that guy, right here. If B minus C, if B and C are congruent, then the class of B is same as the class of C, you see? So using that, the statement here, A plus C is congruent to A prime plus C prime mod I, is equivalent to saying that A plus C plus I, the coset of A plus C, is same as the coset of A prime plus C prime. And the coset of AC is the same as the coset of A prime plus C prime. And this version will be better suited for what's coming. So given all this, now I'm ready for the definition. Define two binary operations denoted by plus and dot, as always, on the set R mod I, in the set of these cosets as follows. Given two elements of R mod I need to tell you what the sum of these two things are and what the product is. What kind of creature are capital A and capital C? Well, they are subsets of R. They are sets that look like this for some little a. Okay, so given capital A and capital C, I choose here is the prescription. You choose an element from capital A and an element from capital C. Choose any. Okay, so little a and little c are elements of your ring R. And define A plus C to be the coset of little a plus little c, and A times C to be the coset of little a times little c. So the sum and the product that you see on the right hand side, these are the sum and the product of the ring R, because little a and little c belong to R. And the sum and the product you see on the left hand side, these are the new sum and the new product that we are defining on this set R mod I. The right hand side is the definition of the left hand side. Sometimes that's denoted like this. That you define this thing to be that thing. But there is a little subtlety here. We need to verify that this prescription gives a well-defined binary operation on R mod I. What do I mean? I mean, look at this description. What are we saying? You give me two cosets A and C, all right? And to define their sum, what have I done? I've chosen a little a from capital A and a little c from capital C. And then I just say that the sum of capital A and capital C is little a plus little c plus I, meaning the coset of little a plus little c. But instead of choosing this little a and this little c, potentially I could have chosen some other representatives. I could have chosen a prime in A and a c prime in C. And then if I did that, I would get A prime plus C prime plus I, instead of getting A plus C plus I. And here I'd get A prime C prime plus I. But if these things are different, then this definition doesn't make any sense. So these things better be equal. So that's what I need to check. Okay? So that's what I mean by having to verify that this prescription is a well-defined binary operation, or binary operations, because there are two of them. So this is rather crucial, so let's write it down. So what I'm saying is, instead of choosing A and C, A in A and little c in capital C, one could choose some A prime in A and some C prime in C. And one needs to verify that under these circumstances, this does not change the defining expression for capital A plus C and capital A times C, meaning that these two things are the same, i.e. that A plus C plus I is A prime plus C prime plus I, and AC, AC plus I is A prime C prime plus I. But look, A and A prime are in the same coset capital A. Since A and A prime are in the same coset, they're in the same congruence class. Look on the left. If they're in the same congruence class, then they're congruent. So A is congruent to A prime mod I. And similarly, since C and C prime are in the same congruence class, capital C, same coset C, we have C is congruent to C prime mod I. And then this lemma up here exactly gives you what you need. It tells you that A plus the coset of A plus C is the same as the coset of A prime plus C prime, and the coset of AC is the same as coset of A prime plus C prime. So it gives you these things. So by lemma above, we do get A plus C plus I equals A prime plus C prime plus I, and AC plus I equals A prime C prime plus I. And that verifies that the prescription up here actually give you well-defined binary operations on R mod I. And now, so A plus C and A dot C are well defined. That's not very precise, but you know what I mean. And now we'll verify that the set R mod I with these two operations, form a ring, and that would be called the quotient ring.